In this video, I'm going to go through a one sample t-test for a population mean, and I'm actually going to walk through the same problem twice. So my plan is to first just solve this problem. I'm not going to explain a ton of the details, and I'm not going to really go in depth as to how things would be different if some specific thing were changed. And after I do that, I'm going to go back through the problem and really flesh out some of those details, talk about how things would be different. And my intent is that if you're watching this video to refresh yourself on how to do a one sample t-test, I think the first part will be plenty. And you may pick through the second part to find little things. But if this is your first time seeing it, you'll still want to watch the beginning, watch me go through it, but you'll probably have lots of questions. And then hopefully when I go back through it again, those questions will be answered. So let's get started. So in this problem, a sports equipment company claims that the average lifespan of their new tennis ball is 60 hours. A sports store thinks that this is an overestimate. To test their suspicions, they take a random sample of 20 of the tennis balls and measure their lifespans in hours. The values are below. So we have these 20 values of lifespans in hours listed. And the question is this evidence that the average lifespan of a new tennis ball is less than 60 hours? So the first step I'm going to do here, I think is maybe a bit weird if in the context of this course, but I'll explain this all later. So I always start with step 0. So step 0 is to figure out what procedure we should do. And this seems a bit weird because I already told you that we were doing a one sample t-test for a population mean, but I'll address this later. So the question is a yes/no question about a population mean. So the question being this question. So this is a one sample t-test problem. So that's step 0. I decide what I'm going to do. Step 1 is to state my hypotheses. So step 1, my null hypothesis is that the true average lifespan, the true population mean, is 60 hours. And my alternative hypothesis, since they're looking for evidence that the average lifespan is less than 60, is that mu is less than 60. And I always like to add a hypothesis in words. So this is saying that the average lifespan is 60 hours. And this is saying that the average lifespan is less than 60 hours. So that's step 1, state my hypotheses. An A there. All right, so step 2 is to check conditions. So I have 3 conditions. I have my randomization condition. And as I scroll up, we're told that this is a random sample. My second condition is independence. My independence condition is that my sample size is at most 1/10 of my population, or we often state it as the population is at least 10 times the sample size. And so I always say what the population is in this condition. So the population is all of this new tennis ball ever produced by this company. Now, I don't know how big that population is, but it's reasonable to say or to assume that that population is more than 200, right? That is, I mean, who's producing a tennis ball and producing less than 200? So presumably, this is more than 10 times the sample of 20 tennis balls. So my first two conditions are satisfied. And actually, I think it's useful to put a little check mark next to the conditions that are satisfied. If something wasn't satisfied, I would put a little X next to it, even if I said that in words. And then finally, I have a condition on the date. So in this problem, my sample size is 20. And so that's a medium sample size. So for our purposes, a medium sample size is a sample size between 16 and 40. And I see that you can't really see this here, so let's just move that. So our sample size is medium. And for my condition on data, since it's a medium sample, I need to confirm that there are no outliers and that at most there is slight skew. And so what I'm going to do is I have this data set written as a comma separated list. So I'm going to paste it into RStudio. And I actually need to name it, so I'll call it tennis. And something happened here. I'm not sure why. Let's just try again. Okay, so that seemed to work fine. Not sure what that was all about. So I've entered this data set, and I'm going to do some calculations with it eventually. But for now, what I want to do is check out a histogram of this data set. And I also want to check out a box plot of this data set. And so let me zoom. Yeah, so let's do this. So let's start with the histogram here. Not really sure why this. Let me resize a little so we can see the whole thing. So that's a little better. So this is the histogram of the tennis data set that I was looking at. This looks to me to maybe be slightly left skewed. So I'll say this is a slightly left skewed data set. The tail goes out a bit longer to the left. And then when I go to the box plot, the big thing I'm looking for right now is, are there outliers? I don't see any outliers, right? That is, there aren't any outliers. Those would be represented as little circles. So we have a slight left skew, and we have no outliers. So if we go back here, zoom back where we had it, what we've concluded for the condition on data is that we have a slight left skew, and we have no outliers. And since it was a medium data set, this is what we needed to check. We needed to check skew and outliers. We needed at most slight skew, or roughly symmetric would be fine as well. And we needed no outliers. So this is also satisfied. So all three conditions are satisfied. Now I'm going to go to step 3. So in step 3, I'm going to do some calculations. And I'm going to do my calculations in RStudio. So first I need to know my mean. So that's x bar. So I have x bar is 57.31. And I also need to know my standard deviation. Type in SD. I get a standard deviation of 7.545. And I'm not being particularly careful with rounding, but you should always be a little careful to include a few more decimal places than your ultimate answer needs. And in particular, if you get a wrong answer, one thing to check is your rounding error. So I have X bar, I have S, and the things I need to calculate in step 3 are my test statistic T. So X bar is 57.31. Mu naught was this thing, the number that appears in the hypotheses. It's always the same number. It's 60. S is 7.545. And here, N, the sample size was 20. And I'm always really careful typing this in. The numerator has to be in parentheses. And the denominator has to be in parentheses, right? I want to do this division before the other division. And I get minus 1.59. So that's T. Quickly add a blank page here so we can continue this calculation. I don't know why it's smaller than the previous page, but that should be okay. So yeah, so I got these numbers, and now I need my p-value. And so to calculate my p-value, I'll need to get the correct command in RStudio. And in order to do that, before calculating the p-value, I want to draw a picture. And so I'm going to draw a picture, and the t-distribution looks visually like a normal distribution. It's a different shape. The tails are a bit fatter, but I just need to draw some sort of bell curve and a 0 in the middle, and that puts my t-value down here. The average t-value is 0. The one I got was minus 1.59. And I need to shade in the area that represents my p-value, and that's determined by the alternative. So I go up here, and my alternative is less than, so I want area to the left. So I'm going to go shade that in. That's the area that I want for my p-value. And what is that area? Well, in this case, it's relatively straightforward. Because it's area to the left, the RStudio command pt just tells me area to the left. So I just need to type in my t-value and my degrees of freedom. My degrees of freedom is 19 because my sample size is 20. It's always one less than the sample size. Let's see what that is. I get 0.0642. That's my p-value. And now I'm on to step 4, which is my conclusion. And the problem didn't state this, but I'm going to make, when I'm not told what my conclusion should be based on, we need a significance level. I, as a default, think alpha equals 0.05 is a good choice for a significance level. And this p-value is greater than alpha. So p is greater than alpha. And when p is greater than alpha, we fail to reject the null hypothesis. Now I have to say what that actually means. And I always like to look at my hypotheses. So failing to reject the null hypothesis is saying that we don't actually have any evidence for the alternative hypothesis here. And so when I fail to reject this null hypothesis, what that means is that we don't have strong evidence that the average lifespan of these tennis balls is less than 60 hours. And I'm finished. Steps 0 through 4. Step 0 is really for yourself, but steps 1 through 4 are usually the things I want to see. That's an entire t-test, start to finish. All right, so I think that took a little bit longer than I had hoped, but that's kind of always how it is. Let's go back to the top and talk through a few more details. So step 0 is the first thing I'd like to address. Step 0 is something that is going to become more and more important as the course moves on. Right now, we have literally, well, maybe we've seen 2 procedures, but they're really kind of the same thing, right? The t-test is a more general procedure. All we've ever done is hypothesis testing for a population mean. But by the end of this course, we're going to have, like 8 or so different hypothesis tests. We're also going to have things known as confidence intervals. And one of the trickiest things that you will have to be able to do is take a problem like this and determine which procedure you should use. And I tend to think that it does you a lot of benefit to, from the beginning, start to think about this step 0, even though you know what it's going to be, right? That is all we possibly could be asking you is to do a 1 sample t-test. But it's worth asking yourself, hey, why is this a 1 sample t-test? In this case, it's a hypothesis test because it's a yes-no question, right? Yes-no questions about populations are generally answered with hypothesis tests. And it's referring to a population mean. It's referring to the average lifespan of the tennis balls. So that's my step 0, is really just understanding what the question's asking. In step 1, I have to state hypotheses. My hypotheses are determined by the context of the problem. My null hypothesis is that mu equals 60. The reason that my null hypothesis is that mu equals 60 is that's the baseline value. This company is claiming that their tennis balls have a lifespan of 60 hours. And that's the thing we're trying to show isn't true, right? We're trying to show the lifespan's actually less. And that's why the alternative is less than. Right? This is the thing that the company or that the sports store wants to show. They have this suspicion that the tennis balls don't have as good of a longevity as the company claims. They're trying to show that it's less than 60. I like to write it both in symbols and in words because my feeling is that the symbols help you with the computation, as I'll maybe explain as we move down, and the words help you when you eventually have to make a conclusion. So writing it both ways can be really useful. Moving on to step 2. Okay, so step 2, I'm gonna actually go to a different page because the conditions are one of the trickiest things to learn in this course. In particular, they just don't get tested well in WebAssign, in online homework, right? It's hard to make you write out these conditions. But what we'll see is that we'll go through all these different procedures and they'll all have the same 3 conditions: randomization, independence, and a condition on data. And for the most part, these top 2 conditions will always be the same. Even as we're doing all of these different scenarios, different types of situations, the condition on data is what's going to vary. So let's quickly hop over to a different screen and talk about these conditions. So in this example, we had a random sample, but that's not always going to be the case because experiments, we never have a random sample, or we almost never do. So for randomization, what we need is an observational study that uses a random sample, or we need a randomized experiment. And so it's important that when you're verifying the conditions, you actually determine which of the 2 is going on, or maybe none of them are going on. That is, there are plenty of situations in which you have no choice but to use a non-random sample, or you have an experiment that somehow you can't randomize. And so maybe the randomization condition's not satisfied, in which case you could say that. You could say this is an unrandomized experiment, or you could say this is an observational study, but it doesn't seem like the sample's random. So that's what we need for randomization. Our independence condition is often stated as that the population is 10 times the sample. And what I usually want to see for this is tell me what the population is. So in this case, you would say the population is all of these new tennis balls ever produced by this company. And say if you think this population is 10 times the sample. In this example, I think the only reasonable choice for a population is all tennis balls produced by this company. And I think that it's the only reasonable thing to say is that, yeah, that has to be more than 200, right? No one's going to design a tennis ball and not produce 200 of them. But in lots of problems, this is going to be somewhat up to interpretation. That is, if you're only given a few words about a problem, you might not really be told enough to be certain exactly what the population is. You might say, wait, are they talking about adults in the US, or are they talking about all people in the US? Or are they talking about just adult males in the US, or something like that, right? There are problems where it's not totally clear what the population is from the amount of information you're given. Just tell me what you think it is. And as long as you've made a reasonable choice, that's fine. And again, same with this. Tell me whether you think it's 10 times the sample. And in most instances, it'll be relatively clear, but if it's not, that's fine. A reasonably explained answer is fine with me. All right, the final condition is the condition on data. And so as I said, the first two will always be the same throughout the different types of problems that we do. That is, randomization is always random sample or randomized experiment, and independence is always that we need a population 10 times the sample. There are some details in there sometimes, but you'll get really used to these. The condition on data is a specific thing to each type of procedure. So in this case, it's a hypothesis test. And the key to understanding the condition on data is it's all a question of how big our sample is. So if our sample size is less than or equal to 15, we need our distribution to be roughly symmetric with no outliers. If our sample size, and I often call that small, if our sample size is medium, so 16 to 39, then what we need, that's what we saw in this problem. I often say at most slight skew. So roughly symmetric is fine, slightly skewed is fine, but strong skew would be a problem. And we also need no outliers. And if we have a large sample, so a sample of size at least 40, what we need is no extreme outliers. So any amount of skew is fine. It would just be if you have outliers that are just way, way outside the regular range of data. And again, when you're checking this, it's conceivable that we'll have a medium sample size, for instance, and there will be an outlier, right? In which case you would say, hey, this condition's not satisfied. There's an outlier. So when you're verifying the conditions on data, you want to start with the sample size. That is, tell yourself, okay, this is a certain sample size. What do I need to check, right? So if you have a large sample, you can say, hey, all I really need to do is create a box plot and see if there are any outliers. Maybe there's none, and then I'm done. And if the sample is really small, you'll say, okay, well, I need a histogram to confirm it's roughly symmetric. I also need a box plot to see if there's outliers. So start with the sample size, see what you need to check. You'll notice I'm spending a lot of time on conditions. Again, I think it's one of the things in my experience that people struggle with the most. I wanted to very briefly mention, so if conditions aren't satisfied, that is, one or more of these isn't satisfied, you can still do the rest of the hypothesis test. It doesn't prevent your ability to do all of these computations. And so you might ask, well, what's the point of these conditions? Well, what the conditions are doing is if one of them is not satisfied, it's going to change the way your results are interpreted. And it depends on which condition's not satisfied. So randomization is easiest to understand. If you don't have randomization, then your data from your sample doesn't necessarily represent your population. So if randomization is not satisfied, and sometimes it's not, sometimes there's no way around it, you have to ask yourself, okay, we got this conclusion, but we have to be skeptical that this conclusion is actually representative of the population that we're trying to talk about. Independence is even a bit weirder. Independence is very counterintuitive if you haven't seen this before, because it seems weird that you need your sample to be much smaller than your population. And it's not really worth delving into. It turns out that if independence isn't satisfied, if your sample is actually kind of getting closer to the size of the population, then your p-values and your results will be a bit understated. Or in other words, maybe there was a procedure, not one that we'll do in this class, but there are other procedures that would be more appropriate. You'd want to take into account the fact that your sample was getting close in size to the population. The condition on data is similar, but a little easier to understand. When these conditions on data aren't satisfied, your t-values might not follow exactly a t-distribution. So they might follow something that looks like a t-distribution, but is a bit off. And so if one of these isn't satisfied, you have to be a bit skeptical that your p-value might not be exactly right, in the sense that a p-value is supposed to represent the probability of results as extreme as what you got if the null hypothesis is true. If these aren't satisfied, then that probability is not exactly represented by your p-value. All right, so that was a lot on conditions, but I think it was worth talking about because, again, I think this is a common place that there's not a ton of area to practice it. All right, so back to the calculations. I think the calculation of t is relatively straightforward once you're comfortable with RStudio. That is, it's all about being able to type stuff into RStudio, being able to enter parentheses correctly, and that sort of thing. The calculation of p, on the other hand, is far less straightforward. In this specific example, because our alternative hypothesis was less than, this was the area we wanted, and all we needed to type was pt. But if our alternative hypothesis had been greater than, or it had been not equal to, we would have to do a different calculation. Maybe we would have to do this, but subtract it from 1. Or maybe we would have to double this number. And there's an entire separate video on this of once you have t, how do you find p? It's an important enough thing that I just wanted to address it in its own video. So I'm not going to go any more into that. But it's worth to have in the back of your head is that it's not always just pt. You need to draw the picture. For more details, see that other video. Okay, finally, we're at our conclusion. We need a significance level. The whole idea of a hypothesis test and a significance level, its role is that we're trying to determine, is this p-value big or small? The p-value tells us if the null hypothesis is true, how likely would it be for this thing to happen? And so when we have small p-values, we say, well, if the null hypothesis were true, this thing would be highly unlikely. Seems like maybe the null hypothesis isn't true. And then when we have large p-values, we say, okay, well, this would be a totally normal thing to happen if the null hypothesis were true. This is not at all any reason to doubt the null hypothesis. But we have to decide what's a big p-value, what's a small p-value. That's where alpha comes in. Often you're just given this in a problem. If it's not given to you, 0.05 is a pretty standard number to choose. So in this case, p is greater than alpha, right? This number is greater than this. And that means that p is large, and so we fail to reject the null hypothesis. Our result is not that unlikely if the null hypothesis were true. When we fail to reject, it's not evidence that the null hypothesis is true. And if you take a step back from this problem and pretend you had learned no statistics up to this point, you can actually see why this is true. It's relatively obvious once you step back. It's easy in the problem to not see this. We definitely have evidence against the null hypothesis, right? Our sample had an average lifespan that was less than 60, which is what we were trying to show. And so it's not that we have evidence that the average lifespan is 60. We definitely don't. In fact, we have some evidence that the average lifespan is less than 60. What we do have is evidence that's not particularly strong, right? So we don't have strong evidence that the average lifespan is less than 60 hours, even though we do have some evidence. Just really quickly, if we had rejected the null hypothesis, that would have happened if we got a value less than 0.05, then we would say, oh yeah, we do have strong evidence that the average lifespan is less than 60 hours. So we would have a slightly different conclusion. So one last time, hypothesis test start to finish. We start with our step 0. This is really just for you to decide what type of problem it is and how to answer it. It becomes more important later in the course, but that's where we decide what context are we in, what's an appropriate strategy. We state hypotheses. We check conditions, which are always these 3 things, but in particular, this last one will vary a lot for different procedures. We do our calculations. Those vary procedure to procedure, but I tend to think that you get tons of practice with calculations in WebAssign, and so hopefully that's not too tough to, once you practice a bunch, to get that practice that you need to be getting these right on the first try. And then finally, we state our conclusion. And the big thing with conclusions that I see is when you fail to reject, be careful how you phrase your conclusion in context. Failing to reject is not saying that the null hypothesis is true or even that we think it's true. It's just that we don't really have evidence that it's true. All right, so for those who watched to the end of the video, congratulations. I think that's a really good thing to make it all the way through. I know that it was a bit of a long video, but hopefully you left it feeling like you had a better grasp on, if not all the details of a hypothesis test, on the overall structure, what each piece means, and then with practice and maybe rewatching select parts, you'll be able to kind of nail it down and do a hypothesis test on your own just from a stated problem from start to finish.